called for each x in this, if this is open, it should be true that for each x in U, we find something like this so that the whole is contained in here. This is the definition we want to use. So how are we going to start proving this? First, we take x in this, right? So let x be in this union. Let us go back and look at the definition of this is what we want to show is open. So let us prove number 1. And then number 2 I'm going to leave it for you. So
this can be the induction one.
no.
Oh, whew, yeah.
I'm trying to move away from the logic. I want to go to logic.
Okay.
Yes. So what we know is the following. We said we just take an arbitrary union of collection of open sets. So I'm going to say let ui I in some index I be right. We don't specify what is this, the big I. This is a collection of open sets in R. Right. So we must show that the set, the union, right? I is open set. This is what we want to show. You start with that collection of open sets, and then you want to show that if you take the union of this, this is also an open set. So, who can suggest how are we going to go about this proof?
At any other point you could pick one of the
So
smaller than that.
you come in, you say if k is 2, then you have minus half and half, and then you carry on like that, right? So the intersection will be 0. Yes, this is 0, right? So the intersection will be 0. So is the set open? Singleton, is it open?
No,
Why?
because it doesn't exist in epsilon such that.
It's a singleton and compact set.
Yes.
So, let's say in I, right? We can find k in I such that the x is contained in the UK. Is it true? Right. If it's in the unions, so that should be, yeah, okay. But then what can we say? Now we see x is in the UK, and then this and k is coming from I. What do we know about this UK?
It's open.
It's open. So what can we say?
Since x and k are arbitrary.
So there is an epsilon, right? So there is epsilon positive such that x minus this, x plus that is in this u subset k, right? You agree? But what can we say now?
UK is a subset of
But the UK is a subset of the union, right? Is it true? Therefore, this is also in here. Does it tell us that this intersection is open? Yeah, we done, right? So you see how you get your proof. You go back to your definition. Definition says that we want to show that this thing is open. But the definition says if we take x in this thing, we should be able to get epsilon so that we have this set inside, the open inside. So you always try to use your definition and some reasoning. You see, we started with the definition there, knowing that if it's in this many things, there should be some k in I where this thing is in one of these the open balls. From there, this we know by assumption is open. Then by definition, we can find epsilon so that this is there, but this is contained in that, so this set should be contained, and then it proves our theorem. So that's how you prove. First the definition, what does it say? And then most of the time when I do a proof, especially for the student, I want to see, first, this is what is given and what is it that I want to prove. Because if you don't know what you want to prove, then you are not going to get anywhere. So that's why I repeated the statement here. This is not necessary. You don't have to always write this one. But to make sure that we're in the same page, we understand where we are going. So after seeing that, we go back to the definition and see what we want. Should take x in here, and then we should be able to find an open ball containing this. And then we just use the argument. So the second one, I will leave it as a proof, an exercise to you. Yeah, countable union of these joint sets. Oh, these joint open intervals. Yeah, this is the interval. Yeah. A, let S be a subset of R and X also in R. Then we say the following. Number A, some of you have seen this. X in S is called an interior point. Interior point of subset S if the following happens. If we can find epsilon positive such that alright. So that's the definition of the interior point. And then some people they denote it like that. Or the interior of this number S with an empty interior. Rationals.
Oh,
Yeah.
yeah. Of course.
It's rationals.
Wait, what set was this where you couldn't draw this ball?
Which one?
That set.
Irrationals
Yeah, that one.
is the one.
You can't find an interior point because you can't draw a ball around at any point.
Okay.
Yeah. Yeah, I don't know what you need.
I don't think that is.
My head is
Of S, if so, this one is for every the interval, this interval I think there's something that I missed here. In S and a point in R without the number S, right? And there's some alphabet that they use I cannot write. So for the interior there's some funny thing like that. Yeah. What?
Oh,
If you have
rationals.
if you have
Where's my phone?
Oh, I put it there, sir. Behind you. Right behind you.
Oh, can I ask you something?
The set of natural numbers.
yeah,
Natural numbers.
You're going to contain something that's outside and only should be studied.
Any finite set, any countable.
How many people are supporting the idea of
the natural
Generalization.
Natural numbers.
Any finite.
Yeah, minus one is not the set.
I want you to example of a point which is a boundary of some set.
You can make the interval, if you make any closed interval, you just take two ends. So if you have like 1 and 2, then you just make 1 is a boundary point and 2 is a boundary point.
Yes.
What if it's open in there?
That also. Yes, that's
Still.
Yeah, also do inputs.
So you,
No.
I'm asking about this set. If S
Yeah.
is still, what do you say is still true?
Yeah. 0 and 1.
So the boundary will be 0 and 1.
Yeah.
Because if you draw an epsilon. No, it's true. If you draw an epsilon region around it, you get a point. Maybe on both sides.
Yeah, it's
Give a set that is not.
Isolated. So the isolated point of S if the following happens. If we can find epsilon positive such that intersection with S will give us that. Example? The singleton.
Natural
Let us get a set of So now you take that ball, you intersect with S, and then you only get the point X. What is the example?
a subset of R.
Hmm.
So if we can find a ball,
So we want to
small
get a
enough.
ball like this.
Yes, epsilon is small enough, so it's not.
Alright.
It does not overlap with the.
So intersect it with S, and
Yeah, you
you
can
see
say-
what you get.
It's 7.
7.
Yes.
If epsilon is small enough.
Uh,
Yeah.
is it correct?
Yes.
I'm correct.
7. Wait. How big can epsilon be?
0.1.
It's less than 1.
It's less than 1.
Yes.
Ah, 7. 7. Ah, there's no way.
Let's see when you consider.
Hmm.
7.
So if we take natural numbers, can they work as well? Yeah, this one is easy to work, right?
So let's skew out natural numbers like that.
Yeah. So we have seen the examples now. boundary point of A. Is this correct? So if you take a point, this point is either in the interior or the boundary.
If it is in A.
Uh,
What about this isolated point we just defined?
That's boundary.
Is a boundary?
yeah.
Oh. No, I see.
So let us try to give a proof, right? Yeah, it seems that will be done shortly. So the proof says the following. I do it this way. Let me take A in A and suppose that A is not an interior of A, right? Because here is or is interior or boundary. So I want to prove that. So first I suppose it's not the interior. So it should be the boundary point. So how do you go about this proof?
There's no gate.
You negate the definition. What's the definition of the interior point so we can negate? So we can say, is it for all or is it this?
At least one.
Negation will become for
The negation becomes for all.
Yeah.
So
Oh, is this one?
It's not an interior point if for all epsilon base.
So for every epsilon positive, what do we say again? What's the definition? Contains a point in R without A. Right. So we negating it. Well, are we done? Are we done? Why do we say we are done?
Because in the beginning we said A is light.
A is already in A, right?
So we have another point that is in the complement of A, and it cannot be A.
Mm.
So,
So yeah.
2 points.
Do you understand, guys?
No.
Why you don't understand? It's the definition. Look at the definition of the boundary point. Where should
Yeah. Oh, there's another point. I see.
we- Yeah.
It's just that I couldn't see it there. So.
Okay. This contains a point in S
As
and in
much-
R without S. So this is exactly there.
Oh, okay.
A is there, and then if its complement that's a complement. Can you remove the thing? If the complement is open, right? So there are so much with open sets. So let us look at few examples now. Is this set closed?
Yeah.
Huh?
Yeah.
Why?
This is
Because if you draw
projector.
the complement of that set, you get a union of open
Is the
sets.
light.
there's a cycle.
What is that?
Yeah, it's this light.
No, it's the bit closed.
But look at here, it's fine.
Right. Because the complement will be minus infinity 1, right? Let's go back to our friends. The set Q. Is it closed? Is this one closed? Why? What can we say about this set? Is it closed or open? 1 over n. Hmm.
That is a subset of Q. A subset of Q, so therefore it's not closed.
It's not closed.
Yeah.
What about this one?
It's a subset of Q. It's still not closed because the union of closed. Yeah, the union of closed nets.
No, let's think about this properly.
Wait, you do the complements of that.
The complement is open because it's a union of countable collection of sets.
So this is closed, right?
Thing. Yeah.
Yeah, this is now closed because the complement would be this 0, and then I think it's 1 to infinity.
Well, you need the ones in between.
Hmm? Yeah.
The one, yeah.
Yes, we need the ones in between.
Although you can't.
It's a set.
Yeah, it's going to be very complicated.
It's going to be infinite,
Hmm.
but countable.
So this we can write as, let me see what we can take there. Yeah, so it caters for the one inside. Yes.
Yep.
It is.
So those are the numbers in between these thrashing, code, whatever this thing is.
Yes.
Those numbers there.
Yeah. That we're supposed to be is not necessarily
Thanks for watching, guys.
exactly that.